All right, we're going to talk about solar eclipses now. A solar eclipse occurs when you have the sun over here, you have the Earth here, and you have the moon passing between the sun and the Earth, which means the moon has to be in a new phase. So solar eclipses only occur at new moon. And we can do the same thing we did with the lunar eclipses. If you draw a straight line through the moon, from the top of the sun to the top of the moon, and from the bottom of the sun to the bottom of the moon, and you can do on the other side too, here and here. So this is the moon, this is the Earth. This is the umbral shadow. And this outer part is the penumbral shadow. Okay. So, if you happen to be in the umbral shadow on the Earth, you're going to see a total solar eclipse. If you're in the penumbral shadow, you're going to see a partial solar eclipse, meaning part of the sun gets blocked but not the whole thing. Now the challenge with this umbral shadow is this umbral shadow where it hits the Earth is fairly narrow. It's usually only about 100 miles wide. And that can even be less than that. You have to be in that 100-mile wide stretch or you will not see the eclipse. Alright, now if you're in the penumbral, this can be about from one side to the other, this can be several thousand miles long across. So when there's an eclipse, like there was a solar eclipse in 2017 that came right across the center of the United States, well, pretty much everybody in the United States got a partial, was in the penumbral shadow. But you had to be right in the little slot that went from, it started all the way on the coast over in Oregon, went through Idaho, through Wyoming, Nebraska, down through Missouri, Tennessee, all the way across the United States. Because as the moon is moving across the sun, the shadow is moving across the Earth, so it makes a line going all the way across the Earth, and the Earth is rotating at the same time. So all that has to come into play. So the challenge with this is to see a total solar eclipse, you have to be in that umbral shadow, and that umbral shadow hits different places on the Earth all the time, so you don't get to see them very often. Okay? That's why back in 2017, myself and about 4 other professors here in the A&M Commerce, we all rented a van and drove up to Nebraska because we weren't going to miss it because it didn't happen that often. But there is one coming through here, so mark your calendars in 2024. I think it's April 2024. There is a lunar eclipse that comes right through Dallas, right through Commerce. So put it on your long-term calendar. That's the next one that's going to hit the United States, the continent of the United States. All right, now let's look at what happens from the perspective of the sun. So here's the sun, right here. Here's the moon. Now remember, from the Earth, the sun and the moon are almost exactly the same size. The moon is moving through like this, and the direction it moves through varies on where it is in its orbit and all that, but many times it's just like this. So this is what we would call first contact. Right when the moon starts to move in front of the sun. Now then the moon comes over here, and when it hits this far side over here, and if the moon is just slightly bigger than the sun, this is when second contact occurs. Then third contact occurs just minutes later because the moon then covers and then starts to come out on this side over here. So this is third contact, and I know you can't see that difference because it's very, very small. And then over here is fourth contact. So just like with the lunar eclipse, totality occurs from second to third contact. Now, the difference is totality when conditions are ideal, which means the moon has to be closest to the Earth, so it's biggest, covers more of the sun. We have to be furthest away from the sun, which means summertime. And if you lived on the equator, because that gives you just slight advantage, you're slightly closer to the moon on the equator than you are at the poles. That is when you get maximum totality. The maximum you get is about 7 minutes. And it can never be more than that. Average totality is 2 to 3 minutes. Meaning it does not last for very long. But when it does, it's really cool. I have seen 2 total solar eclipses in my life. I've seen the last two that hit the continental United States, which was 1979, it was February 1979, and it only hit part of the United States. It actually hit Washington, Idaho, Montana, and then curved up and went up through Canada, the part did. But I grew up in Montana, and it actually went right through where I grew up in Bozeman, Montana in 1979. And I saw that one, and I was, I think, a freshman in a high school at the time. And it probably is one of the reasons I ended up being an astronomer, because that was so cool. You say it was 2 to 3 minutes, but those 2 to 3 minutes you remember for your whole life because it's so different than anything else you're going to see. And then I saw the one in 2017, which was just a couple of years ago, and it was just as great. It was really cool. And it was about 2 to 3 minutes as well. We were in Nebraska, right on the edge of Wyoming, when we saw that one. All right, so this is how a solar eclipse looks. So let's look at a couple of pictures here. Now, before I get to that, remember I said this is ideal. It's also possible when the moon is furthest from the Earth, it becomes smaller. And so sometimes the moon doesn't cover the sun at all. So here's the sun, and the moon will be smaller than that. So we have what we call an annular eclipse. And in that case, you have the sun here, and then the moon inside of it. So the moon is here, but the moon's not big enough to block out the sun. So what you get is a ring of light around the sun that you can still see, which we call an annulus, which is why it's called an annular eclipse. And that occurs whenever the moon is furthest away, or moon is near apogee in its orbit. So that means it's furthest away from the Earth. And I'll show you some pictures of those. Those are not nearly as exciting because these kind, you have to use eye protection because you don't want to stare at the sun. Even in the middle of the eclipse you have to, because the sun is still letting light come through. Now I want to clear up some misnomers here. Yes, it's bad. It's always bad to go stare at the sun, so don't go stare at the sun. But some people say, oh, it's worse when there's an eclipse. All of a sudden everybody's going to go blind. It's like, no, the sun doesn't put out any more energy during an eclipse. In fact, it's less energy. But the less energy becomes a problem because then people start staring at the sun. And you don't want to stare at the sun ever because it focuses all the UV and bad rays, infrared rays on the back of your retina, and it can actually burn an image on your retina, and your retina doesn't repair. Meaning if you stared at the sun and you saw this like circle, you would essentially burn out the rods and cones in the back of your eye in a circle, and you'd have that blind spot for the rest of your life. So don't stare at the sun without sun protection, unless it's a total solar eclipse, and then during totality, you can look at it without hurting your eyes at all. So during that totality part. All right, let's look at some pictures. So this is as the moon is passing in or going to the partial eclipse. The moon is covering the sun. Notice you get a really nice crisp edge. There's no atmosphere on the moon, so you get a really crisp shadow right on the edge of the sun. Much crisper than the Earth does. And here we're getting close to totality. Okay? And there's some effects that occur during totality that are very neat. Things just because of the conditions of it. So let's write down over here, effects during totality. You can get what's called the diamond ring effect. You also get something called Bailey's beads. And I'll show you a couple pictures of a few other things that happen too. So as we go into eclipse, so this is first contact, but we're not the second contact. This is second contact right here. What you get is you get a little bright spot here, the last kind of spot of the sun, and then you can see the ring around the sun. That creates a diamond ring effect. It occurs right before second contact and right after third contact. Okay? And that really signals the end of totality and the beginning of totality and the end of totality. But if you look over here, you see there's kind of like red spots around the edge of the sun. That's what's called Bailey's beads. What it is the moon is not nice and perfectly smooth. It has craters and mountains and all kinds of stuff. And so the light is sneaking through those little valleys, and it makes a string of it called Bailey's beads. That's a very good one. And we also see things that are hard to see unless you have very special telescopes. These are called prominences. And so that's some of the other things you can see. You can see prominences. You can also see planets and stars close to the sun. Now it doesn't get dark like you would see at nighttime. It gets more like a bizarre twilight kind of thing. But any bright object shows up easily. You can see Mercury usually right away, which is hard to see